Welcome everyone. Today we'll present to you how we broke out of the guest environment in VMware and compromised the host kernel. We'll work through the key steps and challenge we overcame to achieve this, demonstrating the power of chaining exploits. Our presentation is divided into three main sections. First, in the VMware and Windows kernel part, we'll dive into the vulnerabilities and exploitation technologies for each. Then, in the training section, we'll wrap it up by showing how we linked these to achieve our final goal. I'm Gwangun Jung, and this is Junoh. We are both part of vulnerability research team at Theory, where we conduct exciting research focused on binary analysis and exploitation. We began this research with goal of competing in Pontoon 2024, focusing on the virtualization category, specifically targeting VMware workstation. The challenge included not only compromising the guest environment, but also escaping privileges through a Windows kernel vulnerability on the host. This inspired us to develop the chain multiple exploits, which we'll be working through today. And in this part, I'll be explaining the vulnerabilities we described in VMware workstation and how we exploit them. Let's begin by introducing hypervisors. Hypervisors, also known as virtual machine monitor, is technology that facilitates the creation and management of virtual machines. It can be implemented as software, firmware, or hardware. Hypervisors typically divided into two types, Type 1 and Type 2. Type 1 hypervisors, often called bare metal hypervisors, run directly on the host hardware. In contrast, Type 2 hypervisors operate as an application layer on top of host operating system. Examples of Type 1 hypervisors include KVM, Hyper-V, and VMware ESXi. For Type 2 hypervisors, examples include VMware Workstation, which is our research focus, along with VirtualBox and QEmulator. Next, let's move on the concept of VM escape. VM escape refers to a vulnerability that allows a guest virtual machine to break out of its isolated environment and interact with the host system or other systems. Our goal was to gain access to the host. We focused on vulnerabilities that could lead to code execution or information leakage. We started by examining publicly available one-day CVEs in hypervisors, hoping to uncover zero-day vulnerabilities. While platforms like Hyper-V do not disclose specific bug details, we concentrated on VMware, VirtualBox, and QEmulator, where more detailed information was available. As shown on the slide, most hypervisor vulnerabilities are found in virtual devices. However, there are cases where bugs have been disclosed in other functionalities, such as RPC mechanism or guest physical address request handling. Based on these findings, we decided to explore the virtual device implementation of hypervisors for finding new vulnerabilities. Through our research, we identified two key vulnerabilities. The first is an information leakage vulnerability in the MVME implementation. The second is a user-free issue in VMware's virtual Bluetooth feature. Both vulnerabilities were successfully exploited, enabling us to escape from the guest to the host. But challenge arose during our work. 2 weeks before the registration deadline, VMware issued a patch targeting vulnerability discovered during the TIAMP Cup last October. Unfortunately, one of our vulnerabilities, which found in MVME, was silently fixed as part of the update. We redirected our focus to a different attack surface, the host guest file sharing feature, or HGFS. We identified a new vulnerability in this component, developed an exploit, and successfully tested in just 1 day before the submission deadline. Let's now dive deeper into the details of what vulnerability we discovered, starting with the HGFS issue. The first vulnerability involved uninitialized heap memory in the host guest file sharing feature. HGFS allows the guest to access the host file system, facilitating file sharing operations. VMware provides two communication channels for this purpose, VMCI and backdoor. Through this channel, the guest can invoke various RPC functions, including those used by HGFS. Let's take a closer look at the root cause of this vulnerability. When the guest reads a shared file from the host, the HGFS file read function is invoked. This function is responsible for handling file read requests as part of host guest file sharing feature. Internally, the HGFS file read function calls the malloc function to allocate a response buffer, which will hold the data to be sent back to the guest. The size of allocated buffer is determined by the protocol version. For version 1, the buffer size is set to hex 41. However, the critical issue lies in how the memory is allocated and initialized. The malloc function does not initialize the memory it allocates, leaving parts of it in an uninitialized state. Let's examine the memory initialization process in more detail using both code and diagram to illustrate the issue. When the buffer is allocated, only a portion of memory is filled with actual response data that corresponds to the requested file. The remaining portion of the buffer remains uninitialized. As a result, data from the host heap data should remain private, can be inadvertently included in the response buffer sent back to the guest. This creates an information leakage vulnerability because the uninitialized memory may contain sensitive data from the host environment. To exploit this vulnerability, we needed to write a client that supports HGFS version 1. The challenge was that HGFS over VMCI, the channel used the communication between the guest and host, is not fully implemented in the Open VM Tools project. Additionally, the official Windows guest tools only supports HGFS version 2, which doesn't exhibit the same vulnerability. To overcome this limitation, we hooked the guest filter driver component in Windows that handled file sharing requests to help us manipulate and trigger the vulnerability. Here's how the process works. When a shared file is accessed through the Windows file system, the filter driver generates an HGFS version 2 request. This request is sent to the host via the VMCI channel. The host processes the request and returns the result as an HGFS version 2 response. To exploit the bug, we installed hooks within the filter driver to intercept and modify the HGFS requests it generates. The exploitation steps are as follows. First, our hooks intercept the HGFS version 2 requests generated by filter driver. We then modify the request, converting it into the format of an HGFS version 1 request. Second, the modified request is sent to the host via VMCI channel, where it is processed as if it were a legitimate HGFS version 1 request. Because the host processed this as a version 1 request, it allocates the response buffer using the logic specific to the HGFS version 1. Third, once the host returns the response, we extract and back up the uninitialized data from the response buffer to our temporary space in memory. Finally, to maintain compatibility with the rest of the system, we modified the response back to the HGFS version 2 format so that it can be processed correctly by the filter driver. To further exploit this vulnerability, we needed to identify the base address of VMware VMX module. To achieve this, we sprayed memory with CD-ROM related objects which have a same size as the response buffer and contain the address of VMware VMX module. The rationale for using these objects is that their memory layout often includes pointers that reveal the address of the VMware VMX module. By repeatedly triggering the vulnerability, we were able to get the VMware VMX module address from the uninitialized data returned in the response. If successful, we can obtain the base address, a critical piece of information needed for further exploitation. Let's now discuss the second vulnerability we discovered. This vulnerability is a user-free issue in VMware virtual Bluetooth feature. The virtual Bluetooth feature is designed to allow the guest to connect to the Bluetooth device via the receiver plugged in the host. Since this feature operates over USB, it processes USB request blocks or URBs to handle communication. We identified this vulnerability during our analysis of URB processing logic in virtual Bluetooth device. Let's take a closer look at the root cause of this vulnerability. When the USB controller sends a URB to the virtual Bluetooth device, it is passed to a function called VBluetooth submit URB. This function inspects the endpoint of the incoming URB and then passes it to the VUSBQ submit URB, which adds it a queue for processing. The VUSB submit URB function creates a queue node, stores the URB object address, and appends the node to the queue. The critical flaw here that the URB object reference count is not incremented at this stage. This oversight is where the vulnerability begins. As the queue is processed by VUSBQ handle URB functions, each URB in the queue is iterated over and handled. Once processing is complete, the URB object should perform following up action, such as returning data to the guest or freeing associated resources. To avoid latency, these follow-up tasks are registered as a job to a polling queue, which a worker thread processes later. Now, let's look at how USB reset command contributes to this issue. USB device supports various commands for device management. Among these, the reset command physically resets the device. In the virtual USB implementation, issuing a reset command the reference or pipe object and their associated URBs. The problem arises because the reference counter for the URB object was never incremented during submission. As a result, the reset command frees the URB object even if it's still queued for follow-up processing. Now, let's now break down how this vulnerability can be triggered. First, the guest sends a URB to the virtual Bluetooth device. Once the URB processing is complete, the URB object and handler function are registered as a job, the polling queue. Next, before the polling worker executes this job, the guest sends a reset command to the virtual device via a control type URB. This command resets the device, causing it the referenced and free the URB object while it is still pending in the polling queue. Before the polling queue job associates the freed URB object, we sprayed memory with objects of the same size to occupy the freed memory space. VMware's VMCI feature allows us to allocate controller memory, enabling us to spray a fake URB object in the freed memory region. Here's how we use this vulnerability to achieve arbitrary code execution. The VUSB complete URB function, which processes the URB, calls another function called VUSB complete URB at batch. This function contains an indirect call whose target address is taken from the URB object data. Since we already had the base address of VMware VMX module from the first vulnerability, we used this address to control the URB object data. This allows us to redirect the indirect call to execute arbitrary code. However, there are an additional challenge, control flow guard or CFG. The VMware VMX binary is protected by CFG, which limits the function that can be called indirectly. To bypass this, we construct a return-oriented programming or ROP chain using CFG compatible gadgets. First, we needed the ROP chain to pivot each first argument to the controllable memory region. To achieve this, we redirect the first argument to the guest physical memory space, which is accessible to both the guest and host. An advantage of this approach is that the base address of guest physical memory is stored in the data section of VMware VMX. Additionally, the first page of physical memory remains unused after boot, pivoting a predictable and safe location for our payload. Since we already know the base address of VMware VMX, we can modify the URB object to make the pipe object point to the data section where the physical memory's address is stored. By adjusting a pipe object to point the device object to physical memory, we can gain control over the device object's data. Following the same method described in the previous slide, by setting the device object point to the data section, we can make the vtable point to the guest's physical memory. Once this is done, we can call arbitrary CFG gadgets. The following explains the process of pivoting the first argument of the guest gadget to the guest physical memory. First, we set the URB object data and call gadget 0. This gadget enables us to change the RCX register to a physical memory address and redirect the execution flow to the address stored in the data section. However, since the guest cannot write directly to the VMware VMX data section, we use an additional gadget to bypass this limitation. Next, we select a gadget from the function address stored in the R data section. While there are limitations in the section of gadgets, the gadget we choose only needs to train the next one by using the data provided in the first argument. Now that the first argument points the guest physical address, we gain full control over it, allowing us to manipulate the first argument as needed. This enables us to call any CFG compatible gadget. At this point, system commands could be executed using only ROP. However, we decided to chain a Windows local privilege escalation, as this allows us to achieve a higher reward during the competition. To do so, we crafted the exploit to execute shellcode, leveraging this approach to finalize our attack. Fortunately, our UF vulnerability does not trigger a panic when probably executed, and it can be reliably triggered multiple times. Additionally, VMware VMX loads modules that are not Additionally, VMX loads modules that are not protected by CFG, which further simplified the exploit process. The process of executing the shellcode is as follows. First, we triggered the UF to read the base address of physical memory, which is then used for arbitrary memory read-write operations. Next, we use arbitrary memory reads to obtain the address of virtual protect function and recruit module. Then we select an unused memory space and assign RWX permissions, and then write the shellcode to there. Finally, we execute the shellcode using the jump RCX gadget from the recruit module. With this step complete, we are now ready to escape the VM and execute the Windows RP exploit.
Okay, hi, I'm Junoh Lee. In this part, we'll be discussing a Windows kernel vulnerability that was exploited in the VMware chain. So we'll cover the attack vector and the bug itself with a particular focus on how it was exploited. By the end, you will know how to bypass hardened KASLR and other protection techniques. The vulnerability we'll be discussing exists in the cloud file mini filter, commonly known as cloud filter. This file system filter helps manage files and directories shared on Microsoft OneDrive. Since it is a file system related driver, it includes a large number of functions, around 1,000 in total, and multiple attack vectors. Two primary attack vectors for this filter driver include the file operation filter and the file filter communication port. Additionally, placeholders that manage OneDrive files can also be targeted. This cloud filter has been the focus of several successful exploits, including a blog post from Star Labs and the vulnerability exploited by Synactive at Pon2On last year. Now, let's take a look at how we discovered this bug. The vulnerability occurs in cloud filter's handling of repurse point data, and this attack vector became well known following the technical analysis of CVE 2021-31969. Last year, another in the wild vulnerability was discovered in this attack vector. As we analyzed it, we realized that this was an interesting surface, so we decided to look further, which led us to discover a new vulnerability. Here's a simplified version of the code used for storing repurse point data to be processed by Cloud Filter. Repurse point data can be stored using the set repurse point control in the file system. The repurse tag here specifies the type of repurse point data being stored. If we store data with a tag processed by Cloud Filter, like cloud_3, the system will parse it. When a file operation, such as opening a file, uses repurse point information, the stored data will be processed. Internally, Cloud Filter's repurse point data relies on special structure called HSM data. HSM data contains multiple elements with different types like byte, long, or byte stream, each defined by offset and length. In Cloud Filter's HSM data structure, there are exactly 10 elements. The vulnerability arises during the parsing and storage of bitmap information held by some elements. One of the elements, element 4, can store up to hex 1000 bytes of data. When moving the data of element 4 to newly allocated buffer, there is a length validation, but even if this check fails, copying still occurs. This makes the length validation meaningless, allowing an attacker to pass a value larger than hex 1000 and lead to a heap buffer overflow. Interestingly, there is a routine that validates each element header value before the vulnerable function is called. For element 4, there is a check to ensure the length doesn't exceed hex 1000. However, if element 2, which is a byte type flag, is 0, the validation is bypassed, allowing the vulnerability to be triggered. So, what can we achieve with this vulnerability? First, we can trigger heap buffer overflow in chunk of hex 1000 bytes in the paged pool, where the chunk size is fixed. Moreover, if you check the part that retrieve reparse point data, you will notice it can read up to hex 4000 bytes of data. While more data can be stored due to compression format, hex 4000 bytes is more than sufficient for our exploit. Since reparse point data can store arbitrary data, we can fully control the overflowed content. Now, we know the potential. Let's explore how we use these conditions to build a reliable exploit. The first object we considered for our exploit strategy was the Windows Notification Factory, or WNF object. When WNF generates state data, it creates a WNF state data object, which is commonly used in paged pool heap sprays for Windows kernel exploit. This object is size mutable, and by overriding the data size member, we can gain a powerful primitive. Using this, we can perform out-of-bound write while updating state data, as well as out-of-bound read by querying state data. Initially, this seemed like a straightforward way to complete the exploit. However, if you see the creation of the WNF object, you will notice a max state size check. This limits the size of a WNF state data object to no more than hex 1000. Luckily, since the vulnerability causing chunk was also hex 1000 bytes, it wasn't a problem for object spray. Next, we looked at the state data update function used for performing out-of-bound write. Unfortunately, there is a validation on the data size, which corresponds to the size of the overwritten data, so we couldn't directly use this function in our exploit. If the size of the data to be overwritten exceeds max state size, the function returns an error, meaning an out-of-bound write larger than hex 1000 bytes couldn't be triggered. We then reviewed the state data query function, which is used for performing out-of-bound read. Interestingly, this function passes 0 as the size when validating the data size, meaning that it always passes the validation against max state size. This allows us to still use the out-of-bound read primitive. Given these constraints, we had to find a new object to use in our exploitation. The object we chose was the mail slot object. A mail slot is used for one-way communication between processes in Windows. The receiving thread creates a mail slot to read incoming data, and if no data is received, the thread waits for a timeout. The sending thread can open the specified mail slot path with write permissions to send messages, and the mail slot can hold multiple messages. As mentioned earlier, the mail slot can store multiple messages which are held in the data entry queue. This is quite similar to the data entry used in named pipe. So when a message is received, mail slot allocates an object containing a buffer equal to the size of the data received and associate it with a mail slot context object as part of the linked list. Let's look at how the mail slot data entry object helps in exploitation. First, this object is size mutable. As you can see from the buffer member on the right, it stores the content of the received data, meaning that you can adjust the object size by varying the length of the data. This is crucial when performing heap sprays in Windows kernel. Additionally, This object contains useful members such as data size and buffer pointer, which we will discuss later. Another important point is that this object doesn't have a size limit. Data size is 4 bytes, meaning that it can handle up to 4 gigabytes, which is more than enough for most of the heap exploits. Finally, because this object is allocated in the paged pool, it becomes a feasible option for exploiting our vulnerability. So, the first primitive is out-of-bound read. We can perform an out-of-bound read by overriding the data size member of the Merslot data entry object. Using Merslot pick, prevent freeing the object and avoid potential side effects. To perform an arbitrary read, override the buffer pointer member of the Merslot entry with a target address. As before, using Merslot pick, avoid premature object freeing. Here, members before buffer pointer are not important for exploit. The Merslot data entry can also be used to obtain critical object addresses necessary for completing the exploit. Among them, the thread object is a very important object in Windows kernel exploit, and the address of the current thread can be obtained through this primitive. To create this primitive, we need the arbitrary read primitive mentioned earlier. Since Merslot data entry is a linked list structure where entries are linked to the Merslot context object, reading the data entry list member allows you to obtain the address of the Merslot context. The Merslot context object stores the address of the process object of the thread that created the Merslot. This enables us to obtain both the process and the thread object addresses, which can then be used for token swapping or something. Next, let's discuss arbitrary nullification. Arbitrary nullification allows us to set an arbitrary address to 0, which was a powerful primitive in Windows kernel exploit at the time of pwn2own. This can be used to create an AARW primitive by setting the previous mode of the thread object to 0. When a read is performed on a Merslot, the corresponding data entry is freed, and the ms remove data queue entry function is called. If the value of the IRP member is non-zero, the function assumes that it is waiting for a timer and calls the ms cancel timer function, which set the IRP value in the worker context object to 0. This enables us to make the value at any address 0, meaning arbitrary nullification is possible if we manipulate the IRP and worker context members of the Merslot context entry object. This diagram shows how an arbitrary write is achieved through the Merslot object. First, we create a Merslot data entry with the initial write. Then, we leak the Merslot context address by following data entry list to access and manipulate internal members like queue status. By nullifying queue status in Merslot context and triggering a type confusion, we bypass certain checks. Next, we override the buffer pointer with an arbitrary address. Finally, with the second write, we trigger the arbitrary write, copying our data to the controlled memory address using memcopy. Let's see how we use these objects for our exploitation. First, we perform a heap spray to align hex 1000 byte chunks in memory. You might think that it is difficult to arrange 3 different objects in this order, but with large chunks, there is a high probability they will be allocated adjacent to each other after a certain number of sprays. Though segment boundaries could disrupt the layout, the anti-query techniques help maintain the necessary arrangement. Additionally, since this chunk size isn't frequently used by the kernel, it didn't generate noise in our testing. Then we triggered the vulnerability to modify the WNF state data object, then use WNF out-of-bound read to inspect the method object and confirm the heap layout. It is important to note that the large chunk, for example, larger than a page size, was easily reclaimable, enabling repeated corruption. After that, we retrigger the vulnerability to create the arbitrary nullification primitive mentioned earlier. Although we previously discussed that the arbitrary write primitive, we didn't need it for this exploit. However, for the current version of the Windows kernel, it may become necessary as the use of previous mode might no longer be possible. In our scenario, because the vulnerable chunk object can be freed and reclaimed multiple times, all of the previously mentioned primitives can be used, including obtaining critical object addresses through arbitrary read. We leveraged this to create the AARW primitive by overriding previous mode of the current thread object. The final steps are quite straightforward. First, we follow the process link present in the current thread process object to retrieve the address of the init process object. Next, we read the token object of the init process and overwrite the token member of the current process, thereby performing privilege escalation. Now, let's talk about how we chained the 3 exploits discussed so far. Even after gaining control of VMware, chaining those wasn't that trivial as expected. We would like to share the strategy we used to overcome this challenge. To summarize the entire process of chaining, we first execute shellcode in VMware. This allows us to drop and run the Windows kernel exploit on the host PC. However, dropping such a large file presents a significant hurdle. Our goal is to drop a big binary to the host and execute it. So, we decided to leverage conventional memory. Conventional memory is located at the bottom of the physical memory and has enough unused pages to store the LPE exploit. As seen in the diagram, if all bytes in a page are 0, the memory is considered unused. By identifying these empty pages, we can store the exploit. Earlier, we successfully achieved shellcode execution by bypassing CFG in VMware. Building on that, we first opened the file to store the Windows kernel exploit. We then sequentially saved the blocks located in conventional memory to this file. Finally, by using winexec, we executed the saved exploit file, effectively chaining the exploits together. Now, our presentation is finished. Let's see together our point-to-own exploit demo. You can see that our exploit is fail-safe, so we are triggering the vulnerability multiple times. And you can see the elevated system shell on host PC. Okay, so presentation finished. Due to time constraint, I will skip over the conclusion part, which was prepared for formality. Okay, any questions? Sorry? Yeah. You mean KPP? Actually, we bypassed KPP with known tools, so that wasn't the serious problem. Yeah. Okay, if you have questions, you can email us later. Okay, thank you.